Thanks, Kelly. Good morning or good evening, depending on where you might be in the world. My name is Ted Smith. Um, I am a senior field applications engineer supporting the sensor business here in North America. I have about 20 years of experience in power electronics and sensors um, at companies such as Avago, Lem, Fuji Semiconductor. So today, I would like to discuss current sensing. We'll start out at a high level, talk about a system level overview. We'll then move on to ways to achieve cost-effective isolation for isolated current sensing. We will discuss the differential Hall principle, talk about thermal challenges that may arise in designs, and then how to trade off noise and bandwidth and easy implementation techniques. So to start off, again, from a high level, this is a three-phase inverter. In this case, it's from a variable frequency drive. But I like to use this three-phase inverter as a kind of generalized power electronics architecture because it is essentially the structure of many, many things like UPS systems, like I said, drives, things like solar panels, solar inverters, even like a two-phase inverter if you just cancel out one of these phases. So we'll use this as the structure to talk about where and how current sensing exists in these types of applications. So the first and simplest type of current sensing that is commonly implemented is a low side current sensor. So a single current sensor on the negative bus, which senses all of the load current as a sum, but it cannot really, using this implementation, you can't tell what the individual phase currents are. So this is good for a sum load current, but if you need to reconstruct your phase currents for control, this is really not suitable. The big advantage of this type of design is that it only requires one current sensor and it doesn't need to be isolated. So we're on the negative bus here, and generally the digital logic is grounded to this negative bus. If we want to take this one step up, we can actually use three current sensors. Again, no isolation needed because we're referenced to the negative bus. In this case, we can see the phase currents with the exception of the freewheeling currents that's coming through the body diode of a MOSFET or the anti-parallel diode of IGBTs. But with some work in the microcontroller, we can reconstruct what these phase currents are. And this can help us for some basic feedback control. Again, no isolation needed, and the downfall, I would say the big disadvantage of this type of implementation, other than not being able to see the, again, the freewheeling current, is if there's a phase short to ground. So one of these phases, let's say if this was a motor, one of the internal wires contacts the case and there's a ground fault, the current path comes from the positive side down through the switch into the motor, into earth, and it could destroy your application, destroy one of your switches, or even have put someone in danger before we know that current, that short circuit took place. So the kind of penultimate for phase current sensing is to actually put the current sensors on the phases themselves. Now we sense those short circuits because we can see the current coming through the phases. We don't even need to reconstruct the phase currents. We have them deterministically. We know exactly what the phase currents are. And this is suitable for things like field-oriented control or space vector control. The caveat here is that we need isolation because these phases are now, at usually some hundreds of volts based on this bus voltage. So if this is an offline application, 120 volts offline, you get, around 140, 160 volts DC bus. And we need to isolate that from the digital portion of the design. So let's take a look at what that looks like. Here I've got the power portion of this design in red, the digital portion, the microcontroller, in green. This is 3.3 or 5 or 1.8 volts. And this is, again, anywhere from 60 to maybe a few hundred volts. To isolate the microcontroller from the power electronics while keeping contact, because we need to drive these gates with the microcontroller and we need some feedback, some current feedback to drive that intelligently. First thing we're going to do is look at the isolation on the switches. For lower voltages and for non-safety critical designs, we could just rely on the gate oxide of the FETs or the IGBT. But most of the time, we'll actually use an isolated gate driver. And so that isolated gate driver, those will be connected to the microcontroller, and then we'll intelligently switch these 6 switches. But in order to close the loop here, in order to have that intelligence, we need to know what these phase currents are. And that requires isolated current sensing. So we'll have phase current sensors that are isolated from the high voltage. A few different options on what those isolated current sensors could look like. First of all, we could use a current transformer. These guys are quite accurate, and they have isolation because inside here is a closed magnetic core, a primary coil, and a secondary coil. And the idea is, you have a few turns on the primary, or maybe only a single turn on the primary and many, many turns on the secondary, so that we output a significantly lower current for the high current that's input. The problem with these guys is that they only work at AC. The secondary needs a changing magnetic field to drive an EMF, and that means we need to have a changing primary field. So if there's any DC offset or any DC current, a current transformer will reject that. It won't show it on the output. These guys can also be pretty large. One that we have here is almost 30 millimeters, almost 3 centimeters, and that's board space. And then the third issue with these guys is they're expensive. When you have a closed magnetic core and someone winding coils on the primary and the secondary, that's a lot of manufacturing cost and a decent amount of material. So not the cheapest solution. Another potential architecture would be to use just a shunt resistor. And again, if we need the isolation, we'd have to have some type of separate isolated amplifier. The big advantage here is we don't have to worry about any kind of bandwidth roll off, at least on the resistive part. Can't say the same for the ISO amp. But here, this is a simple concept. It's V equals IR. So no matter what kind of current you put through here, whether it's DC, AC, high frequency, low frequency, V equals IR always holds. So very simple implementation. The problem is we're now into 2 components. We need a Kelvin connection across this shunt resistor. And for higher currents, the shunt resistor can be quite physically large because we have to dissipate power and we have to not let this guy heat up too much, because if he does, it changes the resistive, this guy has a temperature coefficient, so it can change the resistivity. Relatively large footprint once we put all this stuff together. And again, this thing will drift with higher currents due to the self-heating. Third example here would be, or third option here would be MPS's isolated current sensor. This is a single part in an SOIC package, SOIC 8, standard package that you can just put on a surface mount board. The current flows in through the 2 primary pins and out through 2 other primary pins. This is all you need. There's no other components required. It's a simple, small solution in a single package, up to 50 amps. And our primary resistance is very, very low, less than 1 milliohm. This thing is also quite cost effective because it's produced using standard semiconductor, standard silicon processes. The potential cons here are that it's limited to 50 amps. we're essentially limited. The amount of current that this thing can handle is limited by the amount of heat that can be generated and dissipated in this very tiny SOIC8 package. So let's look a little bit at what isolation looks like and what the isolation characteristics are between the primary side and the secondary side. Excuse me. So when we talk about isolation, we have two main specifications that we want to talk through. One is so-called VIORM, that's the working voltage for the MPS solution, that's 250 volts RMS. And the other is VISO, that is the peak over current, the peak over voltage, such as a spike that we can handle and guarantee the insulation will not be damaged. The reason there are two specs is that the working voltage determines what you can operate the device at for every day, all day, for the life of the product, and never have any so-called TDDB, time-dependent dielectric breakdown, essentially no long-term degradation of the insulation. If you were to operate above the VIORM, it's possible that over a very, very long time, the isolation could eventually degrade. And these two terms are common and are used across all types of isolators, not just current sensors, but you'll see these in opto isolators and capacitive digital isolators. From a design perspective, what VIORM basically means is this should be the designed operating voltage of your system should be at this VIORM or less. But you don't need any margin here. The margin is the VISO. So we can handle and we test every part for 2200 volts at 1 minute to guarantee that the insulation will remain intact. But for the lifetime of the part, 250 volts. Let's move on and talk about how these sensors actually work on the inside. So we're going to introduce a term here called differential Hall-based sensing. To start to understand how this works, we're going to use a very simplified version of Ampere's law. And that is essentially that B, the magnetic field that is created by a current, is directly proportional to that current. So if I take a conductor and I push a current through it, I will get a magnetic field around that conductor according to the so-called right-hand rule. So if I use my thumb to point in the direction that the current is going, and then I can curl my right-hand fingers around, and you'll see that if we drive a current through a conductor, we'll get a clockwise rotation of the field here. And we use that inside the MCS parts, inside the MPS current sensor parts. So the primary here, one side of the SOIC8, this primary side is not touching or connected to the die, the silicon die, in any way. There's a gap, as you can see on the side view here. So here we're just taking this picture and flipping it up. So we're looking at the side, and you can see there's a gap here, and this is actually filled with insulating material. So the primary current, the primary voltage never touches the secondary die. This side here, that's colored in a more silver, is the secondary die, and that is attached by copper bonds to the silicon die. When we drive a current into the primary pins from the bottom, you can see what the current path kind of looks like. The important part is this very weird kind of infinity-shaped primary path. This concentrates the current into a very high current density at this point right here. And due to that right-hand rule, we see a magnetic field in blue, and those magnetic field vectors are rotating in a clockwise direction. What that means is that the Hall sensors on this side, we'll call sensing point 1, are seeing a magnetic field in the up direction. And this side here is seeing a magnetic field in the down direction. And if we just make the arbitrary convention that since that up is positive and down is negative, what we'll see here, and again, the side view, you can see the current is now flowing into the screen. The convention that positive is up means that B1 is positive and B2 is negative. So B1 minus a negative B2 is essentially B1 plus B2. And that is the measurement. It seems potentially overly complicated to do it that way, but the reason for that is so that we have external stray field immunity. So in the case of a stray field, a field that could be caused by a close by inductor or any external magnetic field to the application, maybe a high current on a bus bar that's nearby, we'll see a stray field in a single direction instead of this rotating target field. When we see the stray field, now B1 and B2 are seeing the same field in the same direction. And so B1 minus B2 is 0. So we essentially remove that stray field. And then just to illustrate again what the target field looks like, the target field now in green, we have B1 positive, B2 negative, or if the current was coming out of the screen, we'd be rotating the other way, B1 negative, B2 positive. Either way, we end up with a positive or a real term, a non-zero term for the target field, whereas the stray field always cancels to 0. As far as thermals are concerned, I mentioned earlier that the primary path resistance is very, very important. So one of the issues that we have with shunt resistors is throwing a few milliohms into the path of the primary current. So one of our big advantages is having a very, very low resistance on our primary path. If we take, for example, a 30 amp load, remember that power dissipated is equal to I squared R. So 30 amp load is 30 times 30 is 900, but then luckily we're multiplying very, very, very small term, 0.9 times 10 to the minus 3 ohms. And so we get less than a watt of power dissipation, 0.81 watts. This means that we'll have a relatively small die temperature change due to internal heating. And that's important because we want to be able to operate up to 125 degrees Celsius and make sure that the die temperature doesn't go over 150 degrees. So in our example here, let's assume we're operating at 85 degrees Celsius. We have 30 amps going through the primary, and that means that they'll see a die temperature of 120 total degrees based on this 30 amps and the 35 degree temp rise. This graph, by the way, can be found in the data sheet that shows, and of course it's an exponential rise due to the I squared term. So you can calculate at any primary DC current what the self-heating would be and then limit the ambient temperature or limit the primary current based on the ambient temperature based on that graph. One other feature that we implemented is the ability to configure bandwidth. The full bandwidth of our part is 100 kilohertz, but it's possible to reduce that bandwidth by placing a small capacitor on pin 6, the filter pin. And one might ask, why would we ever want to reduce the bandwidth? And the answer is this graph here. As we reduce the bandwidth, we also reduce the input referenced noise. So for high dynamic range, in other words, if you want to be able to sense 30, 40 amps, but also be very accurate at 2 or 3 amps, it could be useful to reduce the bandwidth. So we'll give a couple examples here. At full bandwidth, you can see that we have 63 milliamps of noise. This is essentially white noise, thermal noise from the Hall cell and the amplifier. For an application where we would maybe want to switch at 20 kilohertz and we want to respect the Nyquist frequency, so we set our bandwidth of the part to 40 kilohertz, we've now reduced the noise to only 45 milliamps. And then in a case where we're only sensing a DC current or a very, very low bandwidth, less than 1 kilohertz, we're all the way down to 5 milliamps of input referred noise. So this is a nice trade-off that's available in order to trade off bandwidth for input noise, input referred output noise, I should say. Last thing I'll talk about is our system interfacing by using a ratiometric output. What ratiometric output means is that the output is based on VCC. So with no current flowing through the primary, the output will sit at VCC over 2. This means for a 5-volt part, 2.5 volts, or for a 3.3 volt part, 1.65 volts. And it will rise or fall from there depending on if there's a positive current or if there's a negative current flowing through the part. If we take the MCS 1803 for an example, the 1803 has a 5-volt VCC. So this means that with no current flowing through, we're at 2.5 volts. And we can arbitrarily choose one of the flavors. These guys come in a 5, 10, 20, 30, 40, or 50 amp part. It's the MCS 1803-20, for example, or -30. And let's just, as today's example, use a 30 amp part. It means that if we flow 30 amps through the primary, the output will go up to almost VCC, so minus some small transistor drop. The output at 30 amps is to almost VCC, and the output at 15 amps would be here at basically 3/4 VCC. 1/2 VCC means no current again. The other important thing that I want to talk about here is that if we increase this current to higher than 30 amps, so let's say we go to 40 amps, 50 amps through the primary, it's not going to cause a problem with the part, but the output will rail. The output here is railed at VCC. So you go 40 amps, 50 amps, and you're just not going to get any more output. So if you need to sense all 50 amps, you need to get a 50 amp part. But if you only need to sense up to 30 and you just know that there may be excursions above that, but they don't need to be measured, you can choose a lower current part that fits only the current range that you actually need. All right, so now we're going to take this current back down to 0. As the current slows down, it goes to 0. We get back to VCC over 2, and we now flow in the opposite direction. Here's negative 30 amps or 30 amps in the opposite direction, and we get down to essentially 0 volts. And as we reduce that current again back to 0, we get back to VCC over 2. So that is how ratiometric output works. To reiterate, as a cost-effective solution, we have the MCS series of parts. They all come in a standard SOIC8 surface mount package. It is the smallest solution footprint that you'll find, which require no external components other than maybe a bypass cap if you'd like, and a small filter cap if you want to reduce the bandwidth. If you leave this cap out and leave filter floating, it will just give you your full 100 kilohertz bandwidth. And there's true galvanic isolation integrated into the part with a isolation of up to 2200 volts. All of these parts are available today. Evaluation boards are also available today, and they come in 2 main categories. So we have the MCS 1800, 1801 with 1000 volt isolation and 3% accuracy. The 1802, 1803 are 2.5% accuracy, 2200 volts isolation. And you can see the difference here between these two is that there's a 3.3 version and a 5-volt version. And then coming in 5, 10, 20, 30, 40, or 50 amp trims for each of these parts, and 12.5 and 25 amp trims for the 1800, 1801. All of these parts are pin compatible with each other. They're drop-in compatible with each other. So for instance, you could start out evaluating the MCS 1802-20 and say, oh, you know what? I don't need the accuracy. I don't need the isolation. I'll go to the 12.5 volt 1800 and save some cents. All of these parts can be found at Monolithic Power under our sensors portfolio. Data sheets available online, and these are in full production. Any questions?
Great, thanks, Ted. A lot of good information today. Once again, if you mouse over the bottom of your Zoom webinar interface, you'll see a QA button. Click on that and you'll be able to type in any questions that you may have from the presentation. As we're waiting for those to come in, I'll remind you that we have been recording this session, and both the session and the materials will be available at monolithicpower.com/webinar. And we'll also send you out an email to alert you when those are available. So let's see, we do have a question here. Does the part get damaged if the isolation voltage is exceeded by a short duration of approximately 100 milliseconds?
So it's possible that it could. It depends on what that actual voltage is, but essentially we have to. So we rely on IEC specs to determine what we can put on the data sheet for the isolation. We can only guarantee up to the 2200 volts, the VISO. If we go back to our isolation slide here, sorry, lots of animations. So we guarantee the VISO spec. So for the 1802, 1803, that's 2200 volts peak. If you go to 2201 volts, it's possible, although unlikely, that the isolation could be damaged, even for a short duration. That's exactly what this spec tells us. It tells us that the limit for any duration of a spike is 2200 volts.
Great, thank you. Next one. Are there stray field application scenarios that can affect the device? And then are there application guidelines to work around these issues?
There, in general, due to the differential nature of this part, we will reject external stray fields out of hand. There is one specific scenario, which is, I would say, extremely unlikely, but if there is a high stray field gradient, in other words, if we have a stray field here, and I was trying to get rid of the animation, there we go. If we have a high stray field here, but that stray field has a super high gradient, in other words, the amplitude of the field is very, very high on the left side and quite low on the right side, it is possible that you would see B1 sensing a relatively high stray field, and B2 sensing a relatively low stray field, although in the same direction. And then you would get B1 minus B2 would not equal to 0. B1 minus B2 would equal some small value. The thing that we really have working for us there is that the sensing points are extremely close together, some microns apart. So the gradient has to be extremely high for us to see a differential between B1 and B2. It is possible, and there are application guidelines available from myself or any MPS FAE. We also have application notes, and I believe this one is one that's in work right now. But again, extremely unlikely scenario, but certainly within the realm of possibility.
Okay, next up, what does the output look like after current exceeds the rated current limit?
So if we take a look at this, if we exceed the rating, so let's just look at the smallest current rated part of the 5 amp part. That means that we're gonna hit almost VCC minus a small FET drop. So let's call it 4.9 volts with a 5 amp output. And now we increase the current to 10 amps, 15 amps, 20 amps, 30 amps, 40 amps. That is not an issue. The output is not going to continue to rise linearly because we're at VCC, we're as high as we can go. As the current comes back down now, 40, 30, 20, 10, 5, 4, 3, 2, 1, we get right back on that linear path, and there is no hysteresis whatsoever. These parts don't contain a magnetic concentrator. So one issue that you could see in some parts, non-MPS parts, is that there may be a magnetic concentrator in the part that would be a soft magnetic material that would show hysteresis. Our parts do not have a magnetic concentrator. We rely directly on the bare magnetic field. And so there's no hysteresis. You'll get right back on the linear path, and the output will go right back to the way it's expected to be.
Great. Next up, can the current sensor be used for isolated zero crossing detection for 60 megahertz AC line phase currents?
Yeah, so I think we're talking here about a 60 hertz offline, a standard outlet, and the question is maybe how accurate could we define that zero crossing? So certainly the part can be used for zero cross detection. The question becomes how accurate will that zero cross detection be? And that's where we would take advantage of this bandwidth control. So due to the fact that we're just looking for zero cross and we're only worried about the 60 hertz AC, we would want to throw the maximum, an 80 nanofarad capacitor on the filter pin that would minimize the bandwidth, but would also then minimize the output noise. So now, whereas if you had 65 milliamps of noise, that's your zero cross is plus minus 65 milliamps. Once we put that 80 nanofarad capacitor on, we're down into this situation where and I say in my example DC, but this is really anything under 1 kilohertz. We're down to only 5 milliamps of noise, and so you can get a quite accurate zero cross detection.
Great, thanks, Ted. Looks like that was the last question in the queue. We'll give you just another second here. If you have anything else that you'd like us to help address, please go ahead and put that in now. Okay, I'm not seeing any more come in. Last chance, type quickly. All right, thanks, Ted. It looks like we've answered all the questions. So, all right, see, that always gets them to put one more in.
Oh, yeah.
How does
temperature?
Yeah,
I see. How does temperature affect the noise? So there is a temperature dependency. So we've implemented onboard temperature compensation. So we try to minimize the temperature drift of these parts, but it's not zero. And I'd have to look at the data sheet specifically, and I guess I'd welcome you to go online and take a look at the MCS 1802 or 1803 data sheet. You'll find all the temperature coefficients listed on that data sheet, and I apologize, I don't have them off the top of my head, but there is a minimal temperature drift.
okay. Gone on questions. I don't see any more, so I think we are good here. Once again, thanks everyone for your time today. We look forward to having you join us at future webinars, and we will get you out all the materials from this one within the next few days.
Yep, I'd add my thanks to everybody who attended, and look forward to fielding other discussions. Feel free to go on the website and ask questions in the MPS forum as well, or email us directly.